So the third presenter will be the paper number 148, Mr. Fajar. You may prepare yourself. So the title of the presentation is Study of Increasing Surge Impedance Loading, or SEL, and voltage at Depok substation by changing TASIK-DEPOK 500 kV transmission lines configuration. So the author is Mr. Fajar Triwardana and Professor Rudi Setiabudi from PTPLN Indonesia and also from University of Indonesia. So again, I remind the time for presentation is 12 minutes, but it's better you may finish in 10 minutes, and then the rest will be the discussion. Okay, the time is yours, Mr. Fajar.
Alright, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, ladies and gentlemen. Thanks for the time given to me to present my paper entitled Study of Increasing Surge Impedance Loading (SIL) and Voltage at Depok Substation by Changing TASIK-DEPOK 500 kV transmission line configuration. So, I will so honored to introduce myself here. My name is Fajar Triwardana. I'm from PTPLN Persero. I was graduated from Electrical Engineering Universitas Indonesia, and my professor joined in this paper, Professor Rudi Setiabudi. He is a professor from Electrical Engineering Department, University of Indonesia. Okay, for the introduction, generally, power system is divided into three subsystems. The first one is generating subsystem. Then there is the generator and power plant and all of generating equipments belong. And the second one is transmission system. Transmission consists of transmission line and the high voltage substation. And the last one is distribution system. The distribution system is using to deliver the power directly into the consumers. So, in this paper, we will focus on the transmission system, especially transmission line. So, the transmission line in this operation have several limits, such as temperature limit and surge impedance loading limit. So, in order to decrease the voltage drop, transmission line is using high voltage in this operation. In this paper, we will discuss in 500 kilovolt TASIK-DEPOK transmission line. And time by time, load and generator will increasingly. So the transmission line have to increase its capacity. So, but the transmission lines has several limits. There is temperature limit and surge impedance loading limit. So in this paper, we will discuss the surge impedance loading limit. And the changing transmission lines configuration will change the SIL level. And the study case will take the transmission line in TASIK-DEPOK, which is the transmission lines 500 kilovolt from TASIK substation into Depok substation. So, the theory review is surge impedance loading can be defined as the active power or loading in megawatt unit consumed by a resistive load through a line in which its value is same as the surge impedance value on its line. So, in its operation, transmission line will produce and at the same time will absorb some reactive power. As we can see here, M4 produced is equal to kilovolt square per inductive reactance and capacitive reactance, and the M4 absorbed is equal to current square times to inductive reactance. When the line is loaded and on its seal level, so the M4 produced is equal to M4 absorbed. And we can see in the figure that if the transmission line is loading in its seal level, so it will have zero reactive power produced or absorbed. And by this equation, we get the ratio voltage per current is same as is equal to this characteristic impedance of the transmission line. And the seal can be expressed as here. So the seal depends on inductance and capacitance, and it also depends on the transmission line's configuration. And as we can see here, that inductance depends on two parameters, that is mutual geometric mean distance and self geometric mean distance. This is the equation of the inductance and capacitance for double vertical transmission line. As we using the TASIK-DEPOK transmission line, the TASIK-DEPOK transmission line is using double vertical configuration in operation. So if we want to increase TASIK-DEPOK seal level, we have to close the pass distance, dissociate the subconductor distance, increase the conductor radius, increase the number of subconductor. So the case study, TASIK-DEPOK transmission lines configuration, as we can see here, it is using double vertical configuration, which has 4 stranded conductor for each phase. The line is using Gannet ACSR. By the number of steel and aluminum is 7 and 26. The radius is 0.15 for the steel and 0.20 for aluminum. And the bundle conductor is using quadruple configuration, which has the spacing about 50 centimeter. And the length of the TASIK-DEPOK transmission line is about 280 kilometer circuit. By this data, we can calculate the parameter of the TASIK-DEPOK transmission line is about here. The simulation flowchart that I was done is we have to create. The first one is we have to create the simulation of the Jawa Bali 500 kilovolt transmission system, and the next one is we have to make change to the configuration, and the next is calculate the new parameter by its changing to the configuration, and then put the new parameter into the simulation and running again the simulation, and we can observe the voltage at Depok station. TASIK-DEPOK load flow is from TASIK through the transmission line into Depok substation. So the first one is changing the radius of the Gannet ACSR. So the yellow row is the initial condition about this transmission line, and we can see here we variate the radius both of aluminum and steel conductor. So we variate the steel and aluminum radius to look up the seal value and the percent voltage at Depok substation. And in this simulation, we can see that increase the radius will increase the GMR, or the geometric mean radius of the ACSR Gannet. because of the JMR increase, so the inductance will decrease and capacitance will increase, thus the sea level will increase. And the highest level we can see here, the seal is about 1994. It's achieved when the steel radius is about 0.17 and aluminum is about 0.25. And it changes the subconductor distance. The initial conductor distance, the subconductor distance is about 40 centimeters, and we vary it and we get the value is increase the subconductor distance will increase the GMR, and the inductance will decrease and C will increase to the sea level will increase too. The next one is changing the number of subconductor. The TASIK-DEPOK is using 4 subconductor for each phase. So the other simulation is using 2 subconductor, 3 subconductor, and 6 subconductor. And we get the 6 subconductor has the highest level of seal and the highest level of percent voltage at Depok substation. And the last one is the changing the pass distance. Changing the pass distance is about change to per phase distance and about the horizontally distance of its circuit. And we can get the increased subconductor distance will increase the GMD. L will decrease, C will increase, to stay level will increase. So the conclusion is, on this paper, on this simulation, we get the highest level seal and the boost voltage is obtained when the number of subconductor is 6, while it have a 60 centimeter spacing, and the highest level seal is about 29.45 megawatts, and the Depok bus voltage percent voltage is 96.81%. So this is the all of this table, and thank you so much.
Fajar, very interesting and important presentation. So remind me about basic electrical circuit, ya, GMR and GB. So, but it's very useful for the operation side, yeah, because we always calculate about CIL, yeah, surge impedance loading, and it's very important to maintain the voltage. Okay, is there any question for these topics? Question, please. Yeah, one question. Yeah, we only prepare for 2 questions, yeah. Okay, firstly, Mr. the one with the white shirt, Mr. Harry. Okay, please. Your name and institution.
Good afternoon. My name is Harry from PLN T2B, Jakarta. It's really interesting when we have increased seal, as Mr. Dani said, that we can increase the megawatt without reduce our voltage there. But I think this is the big project. In case that you have to make some changes, right, in the configuration of the tower or in tower in the space between the line. And my question is, do you also consider also the benefit and between benefit and cost ratio for this project? Because it has benefit, but it will take more cost on it. Thank you.
And time.
Directly answer the question.
Alright, thank you for the question. That is a lot of problem with the solution. Of course, the cost, the time for the doing this work, but for in that case, we have to doing some further research, further study of this. So in this paper, I didn't consider the aspect. So in this paper, I just show that the value of if we change the configuration by this value, what the how big and how much the seal and the percent voltage will change. In this paper, I just did this. I think this.
Okay, I think it's quite clear, yeah. Maybe this is in the engineering phase, or maybe if you want to try to do reconductoring, maybe this knowledge will be useful. Okay, the second question, please.
Hello, my name is Kevin from ITB. My question is pretty simple. What are the benefits of increasing seal? Is it only for maintaining the voltage, or are there any other benefits? Thank you.
Alright, thank you. The other benefit for increasing seal is about to increase the capacity of the transmission line. As we can see here for this graphic, if we can make the seal to other point of increase the let's say that is 600 or 800 in this graphic. So the capacity of the transmission line will increase too, and because the seal limited its capacity to besides the thermal unit, the thermal limit of the transmission line. So if we can increase the surge impedance loading, the transmission line capacity will also increase.
Okay, I think because the time also limited, so if you still interested in this topic, you may discuss during the break time. Okay. Okay, again, give a big applause to the presenter. And then Mr. Wakin will give the certificate to the presenter. Please. The